Let's continue our discussion of inelastic collisions now and look at a slightly more sophisticated example now where both objects are moving toward each other. And we're going to do it completely symbolically, and so that way you don't have to do any complex calculations in your head or come up with some nasty fractions that you try and have to come up with. We'll just come up with a nice symbolic answer. So we'll look at the same type of problem here, and we'll assume that both our carts are on the track, only this time we'll say that this cart has a mass of 2m and this cart has a mass of just m. It's a smaller cart. And this cart has a velocity of, we'll say v, but this cart has a velocity of 3v. Okay? So, in what direction is the momentum going to be in? Now, here's where we need to start being a little bit more careful than I've been doing so far or have I talked about, in that momentum is a vector, right? Momentum is a vector, and even though I kind of glossed over that in the first introduction to momentum, you can tell why, because if momentum causes a change in your direction, if it causes an acceleration, then it doesn't necessarily cause a change in your direction, but it does cause an acceleration. It can either slow you down, speed you up, or it will change your direction. And force is a vector. And so if you apply a force to an object and its momentum changes, then momentum must be a vector as well. So we need to define our coordinate system, what direction we want to have our velocities positive in, and what direction we want our velocities to be negative in. Obviously, our velocities are going to be opposing each other, so it's now important to choose what direction is which. And I'll just use the typical convention of the x-axis moving that way. And so that is what we'll do. So if we let the x-axis move that way, and we'll have the negative x-axis point in that direction. And so now we can look at the momenta before our collision and what the momenta will be after the collision, and then we'll be able to define or find the final velocity. So again, if I write out, starting with my condition of conservation of momentum, now the initial momentum here is going to be the sum of the individual momenta before the collision. And let's not forget that these have some Velcro on them, so they'll stick together after the collision. And so the momentum from the 2m cart here is going to be its mass times its velocity in the positive direction, since the direction of your momentum will always be the direction your velocity is, since the momentum is the product of mv. V is the vector in that product, m is your scalar, and so the vector direction will always be in the direction of your velocity. So in this case, the velocity is pointing in the positive x direction, so the 2m cart will always, in this case, will get the positive initial momentum. So we have 2m times its velocity v. The momentum of the second cart of mass m is going to be in the negative direction, because that's the direction its velocity is pointed in. So this will be m times 3v. And that must equal the final momentum. Okay? And I can rewrite this as 2mv minus 3mv, and that will equal my final momentum. And now both of these have the same factors in each, and so I can add and subtract with impunity, and 2mv minus 3mv is negative mv. So what this tells us is that the initial momentum in my system, the total amount of momentum, is in the negative direction. There's more momentum from this object due to his higher speed, even though he has a slightly smaller mass, than this object. And so if I look at both values of the momentum in both directions and then add them up, the net momentum is in the negative direction. All right? And so, again, this must equal my final momentum. But what's my final momentum going to be? My final momentum is going to be the sum of my masses, which is 2m and m, times their final velocity, which is what we are wanting to find. So I want to know what the final velocity of the system is going to be after they collide and stick together. And we know they're now going to be moving in this direction. Okay? So what is that speed going to be? This, of course, is 3m. 3m, not v. And my masses can cancel out, and I'll see that my final velocity, Vf, is equal to negative 1/3 v. So whatever my initial velocity is, my second cart is moving at 3 times that, and so this guy's moving slowly, this object's moving rather quickly, so you have something like this, and then after the collision, both objects are going to be moving in the negative x direction rather slowly. So something like that, right? Moving slowly, moving quickly, and something like that. Okay? So that's what this system is going to do. In the next video, we're going to start looking at the more sophisticated examples of elastic collisions. All right, we'll see you then.